Okay, so we're going to continue on with measurement, and this is the second part of the Chapter 1 PowerPoint presentation. So what is a measurement? Well, the measurement is a comparison of a physical quantity to be measured with a standard unit of measure. So, for example, if I measure my phone and it's 5 inches long, I already have in mind what an inch is. An inch is a standard unit of measure. So when I say, oh, my phone's 5 inches, you have an idea what that means. And we always want to put a unit with our measurement. So, for example, if I measure the length of a table, if I said, well, that table's 27, you would say, 27 what? Is it 27 years old? Is it 27 feet long? Is it 27 inches high? What is it? So we need to know the fixed standard that we're comparing it to. Right, so 27 inches, centimeters, feet, what is it? And so for just a little warning, whenever we're talking in chemistry and science in general, if you have a number without a unit, it's kind of useless. You want to have a unit always related with any number so that you know what you're comparing that number to. Okay, so let's talk a little bit more about measurement. Often the next two words get confused quite a lot. Precision and accuracy. So precision refers to how close the set of values obtained from identical measurements of a quantity are. If I measure the same thing over and over and over again, how close are those measurements to each other? And that is also related to the type of instrument that you're using. So if you're using a ruler that only has feet on it, then if you estimated something that's 5 centimeters long, that would not be very precise because you're just kind of guessing. But if you have if you have inches on there, then you're increasing the precision quite a bit. If you've got tenths of inches, then you're increasing it even more. If it goes down to 1/100th of an inch, then your precision is increasing even more. So precision also has to do with how close, how many decimal places you can have. A similar example, like if we're in the lab, if you take a beaker and you measure some water, those numbers are not very precise. You're getting a really kind of a ballpark idea. So if you want to put 100 milliliters in there, so in a beaker, precision is not very good. But if I take a graduated cylinder and measure 100 milliliters, I'm being much more precise. I'm getting much closer to the actual value in closeness. Then if I really want 100 milliliters, even more careful, there we have volumetric flasks that measure exactly to 100, like to 2 decimal places. So the amount of decimal places is what precision is relating to. Accuracy has more to do with how close to the actual value it is. So you can actually be very accurate but not precise. You can be very precise without being accurate. So give an example of these measurements. So let's say we measured something and the actual value of that cylinder, say that we're measuring, is 10.923. Well, let's say the first set of students measure, get these 4 measurements, 10.536, 10.537, 10.535. You can see you take the average 10.536. Well, that actually is a very precise set of data because you're measuring to 3 decimal places, and your measurements of the same cylinder over and over again are very close to each other, so that is very precise, but it's not very accurate. So probably maybe their ruler was cut off and they didn't know it or something like that. This data set you can see is much more widely spread out, 10.536, 11.365. These numbers are not very precise because they're not repeatable. They're not very close to each other. However, notice that when you average them out, they are very accurate. So actually, neither of these two are very good. We're trying to strive to have good precision and good accuracy, but they don't always come hand in hand. All right, so one way that we can indicate our precision is to use significant figures. And it's a way of indicating to somebody how precise of a measurement you have made. And then if we do calculations with those numbers, how many digits do we keep in order to show that precision? And so significant figures is the way that that's going to happen. So let me explain a little bit more about significant figures. So significant figures are those digits in a measured number or the result of a calculation with a measured number that include all certain digits plus one final digit which has some uncertainty. So let's look at an example of what I mean. So let's say you're trying to measure this steel rod. So you can see that the steel rod is a little bit past 9 centimeters. And actually that arrow falls somewhere between 9.1 and 9.2. So you can see that our certainty is that it's somewhere between 9.1 and 9.2. So you would definitely want to report this as 9.1. Then you're going to estimate one more digit. So that one is probably maybe 9.13, something like that. Someone else might come along and say, oh, well, I think it's 9.12. So that's where the uncertainty comes along, that last digit. So 9.12 is how it would, this measurement would have 3 significant figures because you want to indicate that one last measure of uncertainty. Okay, so that's what I'm saying. 9.12 is considered. What I was saying about precision before, so what if I had a different ruler that only had the big marks, the 1, 2, 3, 4, 5, and had nothing in between? Well, then we would probably only be able to estimate our first decimal place. So if the ruler didn't have all those little marks between, we might only be able to estimate this. We would know definitely that it was between 9 and 10, and we could only estimate that maybe it was 9.1 or 9.2. You wouldn't be able to tell for sure. So that's what I mean by precision, is how well can you measure how detailed can you measure the measurement. So anyway, in this case, 9.1 are significant because we can read those exactly, and then we estimate the third digit, which is also considered significant. All right, so now what if I want to take that measurement and multiply it by something to do some calculation? Well, we have certain rules that we have to follow to keep these correct numbers of significant figures. Sometimes we'll call them sig figs, because these numbers can easily get away from us. So what do I mean by that? So let's say we want to find the density of a piece of gold. So we know that density is mass divided by volume. So you weigh the piece of gold and it's 23.76 grams. And then we measure the volume of it and we find that it's 1.23 milliliters. So what does that mean? Density is mass divided by volume. So if we take that mass divided by the volume, if you put that calculation in the calculator, what do you get? 19.31707,317, maybe some more digits, grams per milliliter. Well, can we really measure it that precisely? Is that really a good value for the density? Oh, probably not, because we don't have measurements that can be that precise. That's too many significant figures. So what you need to do is round. Now we can measure the mass to 4 significant figures, and we can measure the volume to 3 significant figures. And as we'll see on the coming slides, we always go with the smallest amount. So you can see that 19.3 is what you want to round to. We can't really know the density any more precise than that because of our measurements. So we're going to use the rules, the following rules, to help us determine how to and where to round. And just for your information, hopefully everybody knows how to round, but you know that you look at the decimal that you're keeping or the digit that you're keeping, you look at the next digit to the right of it. If it's under 5, you just chop it off. So in this case, there's 19.3, which is where we want to round it to. The next number is a 1, and so we cut it off. If it's a 5 or above, make sure and round up. That's a really big mistake that I see students. They forget to look to see what is the number after where I'm rounding. So let's say we wanted to round this number 19.317077317 to 2 decimal places. Well, then we know it's going to be 19.31 is where we want to round it. So we look at the next digit, 7, that would round up to 2. So to 2 decimal places, this would round to 19.32. So just be careful with rounding. All right, so rules to determine which digits are significant in a measurement. So first of all, anything that's non-zero is considered significant. If you went to the trouble to write it down, it's probably a significant digit. The problems come when you have zeros. So for example, when I measured that the length of that table, was it really 100 centimeters or was it approximately 100 centimeters? Was I, within 100 and 200? Or basically 100, 150, or was it between 99 and 101? How precise was it? So zeros can be really a problem because they could be significant or they could be just placeholders. So that's why these significant figure rules are so important, because we want to be able to indicate that to someone. All right, so here's all the different rules about zeros. If zeros fall between any other significant figures, we always consider them significant. So the number 1.005 has 4 significant figures because we count those zeros. They're between 2 non-zero digits. We count them all. The number 1.03 has 3 significant figures because that 0 gets counted. So zeros between any other digits are always significant. Zeros preceding the first non-zero digit are never significant. So if you look at these two, 0.0026 only has 2 significant figures. The number 0.00206 has 3 significant figures. So you count the 0 in between, but you don't count the zeros to the left. So that's similar to saying, if I wrote the number 005, well, 5 is the only significant digit. Those zeros don't really have any meaning. And it's the same thing here with these, the zeros before any significant digit. All right, now the zeros at the end of the number are the most complicated. And that, again, is because are they placeholders or are they truly significant? Did you mean to measure it that carefully? So if they come after a decimal point, you would consider them significant, because if you go to the trouble to write 100.00, all 5 of those digits would be considered significant, because if you put 0.00, that you're indicating to someone I measured it to 2 decimal places. So those are all considered significant. If there's no decimal point, then those zeros are ambiguous. So, here looking at this, 0.0200, we count all the zeros to the right of the 2. So the 2 and the 2 zeros to the right are considered significant. So it has 3 significant figures. 3.0 has 2 significant figures because we're indicating, yep, I measured that to 1 decimal place and it is a 0. Now the number 10,300, it could be 3 significant figures, it could be 4, it could be 5. It really depends on who did the measuring. So to get around that, we usually like to write things in scientific notation, because then there's only really a decimal point. Everything else is fixed. So scientific notation will often help us. So for example, if I took that 10,300 and I wrote it as 1.03 times 10 to the 4th, then I know I meant 3 significant figures. I meant 10,300. plus or minus. If I wrote it as 1.030, then I know I mean 4 significant figures. Then I meant, oh yeah, I measured that to the tens place. If I put another 0, then I would have 5 significant figures. If it was just one point, yeah. So you get it. So it's the zeros at the end that are ambiguous, and if you really are trying to be very careful with significant figures, the easiest way is to put it in scientific notation. All right, now what if you're trying to do calculations with significant figures? Well, the least certain measurement will always limit the certainty of the calculated quantity. So that should make sense. If I'm trying to get the area of a table and I measure one side to, 0.2 decimal places in centimeters, but then I measure the other one with a meter stick and I just estimate it, well, the area of my desk is only going to be good as the worst measurement, the least significant measurement. Now, when we do a final answer with calculations, we always want to report it. We want the answer to be reported so that, again, there's one uncertain digit. So we use these rules. Okay, so if you're multiplying or dividing a number, you report the result with the same number of significant figures as the measurement with the fewest significant figures. So if you're multiplying a number where there's 2 sig figs and another one where there's 3 sig figs, then your answer should only be in 2. And actually the previous, when I did that density example a few slides ago, notice that the mass was in had 4 significant figures, the volume had 3 significant figures, so my final answer had 3 significant figures because you can't have more than the least significant number in the problem. Now, when you do addition or subtraction, it's a little bit more confusing maybe. You can't have more decimal places than the measure with the fewest decimal places. So, for example, if you measured like I said, if you're adding numbers together and you measure 1 to 2 decimal places and then everything else to 1 decimal place, well, your answer should only have 1 decimal place with the least number of decimal places. I think I have some examples on the next slide. So here, so yeah, you take 14.0 grams divided by 102.4 milliliters, and you plug it in your calculator, that's what you're going to get. So notice that you've got 3 significant figures in the mass, 4 significant figures in the volume. Your answer should only have 3 significant figures, so you're going to round to, the 6 will be your last digit. You look at the next one, which is a 7, so you have to round up, so your answer should be 0.137. The least significant quantity only had 3 significant figures, so you only want to keep 3 significant figures. So I don't want to see answers like this on tests because you'll probably get some points taken off. At the beginning, I'm a little bit lenient, especially, if you're only within 1 decimal off from significant figures. But if you went and wrote that whole thing, you'd be wrong. All right, so here, let's add these numbers together. So let's say, we added 20.4, 1.322, and 83. Well, we can't report this any more significant than the 83 because we didn't bother measuring any decimal places with that 83. So if we add them together, we get 104.722, but we need to round it to 105 because it's the least significant number has no decimal places. So we want our answer to have no decimal places. Now, if you have an exact number, so for example, there are 12 eggs in a dozen. Well, 12 really has infinite number of significant figures because it's 12.00000. It's just an exact number. So if you define a unit or if you count items, you don't worry about the significant figures involved with that. So if you have 9 coins in a bottle, you mean exactly 9. It has infinite number of significant figures. You don't have to round to 1 significant figure if you're multiplying by that 9. If there's 12 inches in a foot, again, that is a unit measurement. Then you mean exactly 12. So if you were gonna convert 52.32 inches and you wanted to convert that to feet, you would divide by 12 inches. You could still keep 4 significant figures that you had in your original number, because 12 inches is an exact number and it's actually got infinite significant figures. So you would keep the same number of significant figures that you started with. So they have no effect on significant figure calculations. All right, so that brings us to some metric units that we're going to also. Chemistry really does a lot with metric units. We don't use the English units, and so I'm just going to do a little bit of an introduction to the metric units. So the SI units, SI basically stands for System International, but it's International System of Units, and I think the actual language for international things is French, and so that's why it's SU, because it's System International, or however you say that in French, and this is what we use in chemistry. So there are 7 base units, SI units, and then all the other ones can be derived. So length is always measured in meters. Now the SI unit for mass is kilograms, although we know that the standard unit, the standard metric unit, is grams. The standard unit of time is seconds. Temperature is in the Kelvin scale, which we'll talk about in a little while. The amount of substance is in moles, which we'll talk about later in the semester. And electric current is amps, which we may not get to for a long time. Anyway, so the top 4 for sure you should pay attention to. Now, you're saying, well, what about volume? Well, volume is considered a derived unit because volume is length times width times height, or length times length, length times length. So it's a derived unit. The advantage of the metric system is that it's a decimal system, so everything's in terms of 10. And then we have prefixes that can indicate what power of 10 we're talking about. So you have on table 1.3, you have the prefixes, and I have on the next slide the most commonly used ones, and you should be somewhat familiar with them. So the standard would be the base unit, which would not have a prefix. If it's 1/10 of the base unit, then it's a deci. 1/100th, or 10 to the minus 2, is centi. 10 to the minus 3, or 1/1000th, is milli. 10 to the minus 6, or 1/1,000,000, is micro. 1/1,000,000,000, 10 to the minus 9th, is nano. Get even smaller, 10 to the minus 12th is pico. Going the other way, if you have 1,000 of the base unit, that's a kilo. If you have 1,000,000 of the base unit, that's a mega. So you put these together and you can see the symbols, and be careful that micro is it's called a mu. It's the Greek letter mu. So it's not an M, but it's not a U. It's kind of a cursive M, mu. But then you put this together with the standard unit. So if you're talking about 1/100th of a meter, you're talking about a centimeter. If you're talking about 1,000 grams, then you're talking about a kilogram. A kilometer is 1,000 meters. A millimeter, a milliliter is 1/1000th of a liter. So you can use these. A microsecond would be 1/1,000,000th, or 10 to the minus 6 seconds. So we put the prefix and the unit together. 10 to the minus 9 grams is the same as a nanogram. 10 to the 3rd meters is a kilometer. 10 to the minus 3 liters is a milliliter. How would we express 6.0 times 10 to the minus 2 meters using the prefix? Well, 10 to the minus 2 is centi, so this would be the same as 6 centimeters. How would you express 3.76 milligrams in grams? Well, you could divide by 1,000 and move the decimal over 3 places, so it would be 0.00376. Or you could also, since milli is 10 to the minus 3, you could always also say 3.76 times 10 to the minus 3 grams. Or you could move the decimal over, but we like scientific notation. Okay, so temperature, the Celsius scale, which is used to be known as the centigrade scale, is the temperature that we use most of the time, in scientific use. Most all the countries in the world, except for the United States, uses the Celsius scale. However, you can see that in the SI base, if you go back to that list, the temperature listed for the SI scale is the Kelvin unit of temperature, and it is an absolute temperature scale. So let me tell you what that means. So temperature is directly related to molecular motion. If you increase the temperature, molecules will move faster. If you decrease the temperature, molecules will move slower. And however, if you get to say 0 Celsius, even 0 Fahrenheit, 0 degrees on most temperature scales don't necessarily mean 0, because at 0 degrees Celsius, molecules are still moving. 0 degrees Celsius is where water freezes, and the molecules are still moving. So that's not considered an absolute scale. Weight is an absolute scale, because if you put nothing on the scale, you will have a weight of 0. So nothing means nothing. So an absolute scale would mean that at 0 we should have no molecular motion at all. And so that's what the Kelvin scale is based on. So it turns out that if you get down to 0 Kelvin, there is absolutely no molecular motion at all. So to convert from Celsius to Kelvin, it's pretty easy. The 0 degrees Kelvin is the same as negative 273.15 degrees Celsius. So to find the Kelvin temperature, you just take the degrees Celsius and add 273.15. So whatever Celsius is, you add 273 to it. And the Fahrenheit scale, as we know, is the present common temperature scale in the United States, and unfortunately we haven't switched over. The Kelvin scale and the Celsius scale are the same scale. The unit of 1 degree is the same measurement. You're just moving it up or down 273 degrees. But the Fahrenheit scale has a different unit degree. And so if you want to convert from Celsius to Fahrenheit, use the right-hand equation. Fahrenheit, you would have to take 1.8 times degrees Celsius and then add 32. So not only is the Fahrenheit scale offset by 32 degrees, the temperature for Fahrenheit is 1.8 times as big. There's 180 degrees between freezing water and boiling water, whereas on the Celsius scale there's 100 degrees between freezing water and boiling water, and so that's why we have to multiply by that factor of 1.8. So if you want to know the Celsius scale and you already know Fahrenheit, you take Fahrenheit, subtract 32, and then divide by 1.8. So this is how you would go back and forth. We'll pretty much stick to Celsius temperatures in this class, but like I said, we may have to use Kelvin from time to time. All right, so like I said earlier, a derived unit is something that uses the base units in some way. So a derived unit, for example, area is length times length. Well, length times width, but it is a measurement of length times another measurement of length. And so area then would be in square meters, meters squared. Volume is length times width times height, which is 3 length units. And so the SI unit would be cubic meters or meters cubed. Just for your information, the liter is the unit that we usually use for volume, and a liter is the same as 1,000 milliliters. And what we should keep in mind is that let's see, a milliliter is equal to 1 centimeter cubed. So if you have a centimeter times a centimeter times a centimeter cubed is the same volume as a milliliter. So if you have 1,000 milliliters, you have 1,000 centimeters cubed. In fact, in medical terminology, when they say you're going to get so many cc's of a shot, cc stands for cubic centimeter. So in fact, it is already in milliliters or cubic centimeters. And then if you take a volume 1 decimeter times 1 decimeter times 1 decimeter, you will get 1 liter. And remember, there's 1,000 milliliters in a liter. So the most common unit for volume is liters. Density is another derived unit, and density is defined as the mass per unit volume. So how much mass fits into a certain amount of volume. So of course, the more mass you have in that same amount of volume, the more dense it is. So there's the formula: density equals mass over volume. And usually if someone says to you, well, a feather weighs less than lead, what they really mean is a feather is less dense than lead, because they're not specifying quantity. So, if I said, if I have a pound of feathers and a pound of lead, which one weighs more? Well, they both weigh the same because I have a pound of each of them. But if density comes into place, well, I have a handful of feathers and a handful of lead, which one weighs more? Well, the handful of lead does, because now you're equating them on the same volume, and so the thing that is more dense will weigh more. So density is mass divided by volume, and you can take this equation and you can rearrange it. So you can multiply, so you can find mass would be density times volume, or you can find volume, which would be mass divided by density. Usually when we talk density units, we're usually talking about grams per milliliter, but it sort of depends on the state of what you're talking about. So usually if it's liquids, we'll say gram per milliliter. If it's a solid, we tend to use grams per centimeter cubed, just because solids are more measurable in that way, although milliliters would not be incorrect. It's just more common for solids to use centimeters cubed. And then often, because gases are so not very dense at all, we often will use density for gases in grams per liter. Just for some comparison, the density of water is 1 gram per milliliter, 1.00, actually water at room temperature. So 1 gram equals 1 milliliter, and that's density is kind of all compared to water. Mercury, there are 13.6 grams in 1 milliliter. So mercury actually is very, very dense, and 1 milliliter of it will be much heavier, 13.6 times heavier than 1 milliliter of water. Air has a density of 1 gram per liter, which is the same as 0.001 gram per milliliter. So you can see it's about 1,000 times less dense than water. Gold is one of the most dense elements, and it's 19.32 grams per centimeter cubed. Density is a physical property, and so it is a characteristic of the substance, but not changing its identity. So density would be similar as color, boiling point, melting point. It's a physical property that can't be changed. Only changes with changing the identity. And here's where I was telling you about density and weight are often confused. Weight is just the amount something weighs, whereas density always has that per unit volume in there. And so here is similar to that story I was telling you. Which weighs more, a pound of lead or a pound of water? Well, they both weigh a pound, and so they both weigh the same amount. Now, if I said which do I have more volume of, a pound of lead or a pound of water? You say, well, a pound of lead is going to be a very small amount, whereas a pound of water is going to be a much bigger amount because it has a much lower density. And so don't get these two concepts confused. Okay, there you go. So let's do a density example. The sample of the mineral galena, lead sulfide, weighs 12.4 grams and has a volume of 1.64 centimeters cubed. What is the density? So luckily, we have our formula. Density is just mass over volume. So we take the mass, which is in grams, 12.4, divided by the density, 1.64 centimeters cubed. We're going to round to 3 significant figures, so the answer is 7.56 grams per centimeter cubed. And since the units don't cancel, you have to keep them both in there. All right, here's another example. Calculate the volume of 65.0 grams of methanol if its density is 0.791 grams per milliliter. Well, this time, so we know density is mass over volume. This time we're looking for volume, so we can rearrange the equation and we can have volume equals mass over density. And so if we put the mass, 65.0 grams, divided by the density, 0.791 grams per milliliter, what you'll notice with the units is that the grams should cancel. And then our final units, we've got 1 over milliliters. So if you invert and multiply, then our units will end up being milliliters. So, and this should make sense. If you want 65 grams and the density is less than 1 gram per milliliter, then to get 65 grams, you're going to have more than 65 milliliters. So 82.2 milliliters is equivalent. All right, so the last thing that we're going to talk about is dimensional analysis. And this is a way of doing conversions very simply. If we use our units especially, it can really make a difference. So it's really good to make sure and use your units whenever you can. Write down the answer with your units, but also keep track of your units. And so, like I said, this is a way of converting, but without getting too confused. So what happens is that the units for the answer will come out of the calculation, and we'll see when we do an example. And if you make an error in arranging the factors, it should be apparent because the final units will be nonsense. So, or at least not what you're looking for. So, dimensional analysis is also sometimes called the factor label method, and it's what we do is we start with what we're given in units, and we want to find conversion factors that are equal to each other, two things that are equal to each other, but with different units. And so, like I said, the units will end up canceling as we go along. So let's start with something that's very simple. Suppose you wish to convert 20 yards to how many feet is that? So you have to know the conversion. 20 yards is what we're given, and we know that there are 3 feet for every 1 yard. And so, but you know, when you're first thinking through this, you say, well, do I multiply? Do I divide? Well, if you multiply by the 3, notice that what happens with the units. You've started out with yards. Now, if you have 1 yard in the denominator and 3 feet in the numerator, you see that the yard units cancel each other. And so my answer will be in feet. So if I'm trying to find feet, I want to make sure that the unit that I'm trying to find is in the numerator, because that one will continue on. So 60 feet. I know that was a simple case, but because you know feet and yards pretty well, but the whole idea of lining the units up, what you're trying to get rid of should go on the bottom, what you're trying to find should go on the top, and then the what you already know and the bottom unit can cancel out. And so you can end up with the units that you're looking for. So the ratio 3 feet to 1 yard is called a conversion factor, and you can make a conversion factor out of any two things that are equivalent but have different units. As long as you know some kind of conversion, and you'll see that we're going to apply this in so many different ways. It doesn't only have to be things like this, English units, or English to metric is another way that we commonly use it. But you'll find out that when you're talking about molecular equations, we can relate different things in an equation by conversion factors, and so we can convert from one thing to another just by using this method. So again, because the numerator and denominator are equivalent to each other, even though they don't look like they're equal to each other, they are equal to each other because of different units. As long as they're equivalent to each other, what we're really doing is multiplying by 1, so the intrinsic value doesn't change. So on that last example, 60 feet and 20 yards are the same, and that's because 3 feet and 1 yard are equal to each other. They just have different units, so the intrinsic value doesn't change. A lot of the times we're going to use conversion factors from English to metric, but like I said, there's just one use of this. But and just for your information, if you're needing to do metric to English conversions, I will give you those conversion factors on the test. You don't have to memorize them. So here are a lot of the really common US to metric unit. 1 inch is 2.54 centimeters, 1 yard is 0.9144 meters, 1 mile is about 1.6 kilometers, etc. Here, 1 mile equals 5,280 feet. I can never remember that, but that's a conversion within the English units. A pound is about 4.4536 kilograms, or sometimes I remember that 1 kilogram is 2.2 pounds. So this is just different ways of looking at it. Anyway, these are helpful units, and there's others that you could probably look up or find. All right, so how do we do this? Well, you start by examining the units you're given, and then the desired unit, and you just find a conversion factor to get you there. Well, what if you can't find a conversion factor? You can always find something that will get you closer. So let's say you were trying to go from feet to centimeters. Well, you may not know the feet to centimeter conversion, but you do know the feet to inch conversion, and then you know the inch to centimeter conversion, and so you can do two different conversions. So that's why we call it factor label, because you can just keep going and multiplying by the next factor and the next factor. So we always take the given unit, multiply by some factor where the given unit is in the denominator and the desired unit is in the numerator. Then the given unit will cancel out, and the desired unit is what we'll end up with. And like I said, if you can't find one, you might have to link together a couple of conversion factors. All right, so what is the length in kilometers of a 500-mile auto race? Well, we need to find a conversion factor from kilometers to miles. And if you look back on that slide, you'll see that 1.609 kilometers is equal to 1 mile. So we know that we're starting with 500 miles. And so that's the unit that we are trying to get rid of. So that's why mile, in this case, in our conversion factor, goes in the denominator, because miles will cancel. And kilometers will go in the numerator, so after miles cancel, our answer will be in kilometers. So 500 times 1.609 divided by 1 gives us 804.7. And then the units cancel, miles cancel, and kilometers are our unit. Like I said before, sometimes you need more than one conversion factor, and you can just string them along until you have what you need. What is a woman's mass in grams if she weighs 115 pounds? Well, you may be able to look up the gram to pound conversion factor, and that's perfectly fine. But what if you couldn't look it up and you had the information from the previous table? Well, we know that there are 0.4563 kilograms in 1 pound. or 2.2 pounds in a kilogram. So we can line that up. So we can actually convert 115 pounds to kilograms, and the pounds will cancel. And our answer is in kilograms, but that's not what the question is asking. The question is asking for a woman's mass in grams. So now we can take that answer and convert it to grams by using a conversion factor between grams and kilograms. Well, it turns out that there's 1,000 grams in a kilogram. So if we take 52.2 times 1,000 divided by 1, we get 52,200 grams. Or to three significant figures, 5.22 times 10 to the fourth grams. We could also just do this all in one long string. Oh, there's the kilograms canceling out, and so our answer is in grams. We could have just started with 115 times 0.4563 divided by 1 times 1,000 divided by 1. You don't have to restart, although if you like to. If you like to do it in step by step, that's fine. But if you like to just do it in one calculation, that's fine also. So here's what I was talking about. So if you take 115 times 0.4563 kilograms per 1 pound, and you already know, well, that's not where I need to be. I need to multiply by 1,000 grams per kilogram. So you don't have to do the intermediate. And my recommendation is, even if you do these calculations on your calculator and you get an answer, don't round it after each step. What I would recommend is doing all your calculations and then at the end round it to the correct number of significant figures, because you'll have less rounding error if you do it that way. There's my pounds canceling, there's my kilograms canceling, and now my answer's in grams. All right, density. Although it's easy to manipulate the formula, density equals mass over volume, you can rearrange it any way you want. But density can also be used as a conversion factor because, again, it's two things that are equivalent to each other. How many grams are equal to 1 unit of volume? So, for example, if I want to know what is the mass of 1 gallon of water in grams, and the density of water is 1 gram per milliliter, I could do the calculation. So 1 gallon, now I have to get 1 gallon of water to milliliters of water. If I know milliliters of water, then I'll know how many, then I know the same number of grams equals that many milliliters. So the first thing I have to do is convert to milliliters. So you can see I start with 1 gallon. There are 4 quarts per every 1 gallon, so 4 quarts. Now I'm going to convert from quarts to liters. Notice that the 1.057 is in the denominator because quarts are what we're trying to cancel out and liters are what we're trying to get. That is a conversion that was on a previous slide. Now we want to know milliliters, so we multiply by 1,000 milliliters per liter, and then we know that the density is 1 gram per milliliter. So notice that all of our units cancel except for the last one, which is grams, and that's the answer that we're looking for. So notice that I have to take 1 times 4 times 1 times 1,000 times 1 divided by 1 divided by 1.057 divided by 1 divided by 1, and that gives me the answer. So just be careful with your calculator also. Every time something's in the denominator, always hit divided by, because you're dividing by that number each time. So just one more note. If you convert a unit that's raised to a power and you're using that conversion, make sure that you raise the conversion factor to the same power. So let's look at an example of that. So the question is, how many liters are in 5.4 meters cubed of water? Well, remember we said earlier that 1 milliliter of water is equal to 1 cubic centimeter, or 1 centimeter cubed. So if we can get meters cubed to centimeters cubed, then we'll be able to convert to milliliters. So if we take that 5.4 meters cubed, notice that every time I convert meter to centimeter, remember I have a cube, and so I have to convert each length, each time I have to convert meter to centimeter 3 times. So meter cubed 1 meter equals 100 centimeters. The next meter also converts to 100 centimeters, and the third meter also converts to 100 centimeters. So my answer will be 5.4 times 10 to the 6th centimeters cubed. The other way you could do that, you can see 5.4 meters cubed. We know that we want to convert from meters cubed to centimeters cubed. We know that 100 centimeters equals a meter, but then if we just cube that conversion factor, notice that the meters cubed will still cancel and the answer will be in centimeters cubed. So just be really careful when you have units that are squared or cubed. If you're trying to convert them, you have to convert each one of them. So now, once we know that there's 5.4 times 10 to the 6 centimeters cubed, and we know that 1 milliliter equals a centimeter cubed, and then so that would give us 5.4 times 10 to the 6 milliliters. And now we know if we want to convert to liters, then we have to divide by 1,000. So 5.4 times 10 to the third liters. So here are some of the things that you should be able to do by the end of this chapter. Describe the scientific method, explain the law of conservation of mass, compare and contrast solid liquids and gases, describe the classifications of matter, for example, elements, compounds, and mixtures, either heterogeneous or homogeneous. Describe the differences between chemical properties and physical properties. Also be able to distinguish between a physical and chemical property or a physical versus chemical change. If I give you one, which one is it? Identify which it is. Define and know the difference between precision and accuracy. Determine the significant figures in a reported measurement. Represent numbers using scientific notation. Be able to apply the rules of significant figures for reported calculated values when reporting calculated values. Be able to convert from one temperature scale to another. Be able to use density to solve for mass, volume, or density if you know the other two. And then be able to use dimensional analysis to convert one unit to any other unit.